Hello, my name is Thomas Prest, and this is joint work with James Howe and Daniel Apon. And James and I will talk to you about how not to design and implement post-quantum cryptography. So post-quantum cryptography is a vast field with thousands of papers. It is also a very diverse field because you can build post-quantum cryptographic schemes from lattices, codes, isogenies, hash functions, and so on. And there are already many good surveys out there, but they usually focus on one family or one aspect of one family. And our goal is not to subsume existing works, and this would be infeasible. Our goal is rather to complement these works. And the way we hope to achieve that is by realizing a transversal approach, in the sense that instead of focus on each family, we abstract away the family and we focus on a four-step process, which is formulating an assumption, designing a cryptographic scheme, implementing this scheme, and deploying this scheme. And this talk, for time constraints, will only focus on two steps, which is designing a scheme and implementing them. But then in the CNRS paper, we also discuss the assumptions. And in the ePrint, we discuss all four steps. And we believe that this approach allows to highlight trends and patterns and also common methodologies, common paradigms, and common threats. And we hope it makes it easier to navigate the sometimes daunting amount of work that is published on the subject. And we also hope that it allows to foster a reusability of ideas, so that if you see a paper in a domain which is not the domain you would usually work on, then you can identify what are the core ideas and hopefully reuse this idea in your own domain. And yeah, this work is half a survey and half a lesson learned paper. So first I will discuss the theory and design of schemes. So if you look at classical schemes for providing signatures and key establishment, well, all schemes can be casted as instantiations of one of four paradigms, which is either Fiat-Shamir or half-dense sign for signatures, and Diffie-Hellman or public key encryption for key establishment. And the good news is that if you look at post-quantum cryptography, even though there are much more schemes and the landscape can seem very complicated, if not confusing at times, then almost all post-quantum schemes, they can also be casted in one of these four families. So by looking at that, one might think, okay, then it's really simple to design post-quantum cryptography. You just take one of these four paradigms and you apply them to your favorite problem. But unfortunately, it's not so simple. And the reason is that if we try to replicate previous constructions, experience has shown that you can end up with either an inefficient scheme, a broken assumption, or both. And again, looking at existing works, the approach which seems the most fruitful is to tweak the paradigms and the problem to fit the assumption, and that the important thing to preserve is a meaningful security proof. And in our paper, we highlight a few examples where indeed the latter approach seems more successful than the prior approach. But in this presentation, I will only focus on one single example. And this example is the example of full domain hash signatures. So because we are at CTRSA, it makes sense to talk about RSA signatures. And RSA signatures, they can be formalized as an instantiation of what is called full domain hash signature. So you start with a message and you pass it into a hash function, then you obtain a challenge C. And then what you have is that you have a pair of functions f and g. So g takes as input the secret key plus the challenge, and it allows you to compute the signature. And then if you have the public key from the signature, you can compute the challenge. and check that it matches the hash of the message. And this is how RSA signatures work, for example. And there are a few theoretical works that tell us that if F and G define what is called a trapdoor permutation, then the scheme that you obtain achieve meaningful security guarantees. And so a natural question is that, can we obtain the same for post-quantum cryptography? Well, unfortunately, it's not as simple because we don't know how to realize trapdoor permutations in a post-quantum world. So there is a work, CFS01, that comes close to achieving such a notion using code, but unfortunately, it has non-scalable parameters. And then there are two works that tried initially to achieve that using lattices, but it realized a weaker notion, and the security proof did no longer apply, and indeed, the schemes got broken. And a solution that was provided in 2008 is the notion of trapdoor preimage samplable functions, or TPSF. And this notion is just weak enough that it can be instantiated from lattices, but it's still strong enough that it still allows you to achieve a meaningful security proof. So it hits just the right balance between being weak and being strong enough. And interestingly enough, 1 decade later, another relaxation called average TPSF was provided. And the good news is that it allows to have even more efficient instantiation from lattices. And in addition, it also allows you to be instantiated from codes. And two prominent examples of schemes derived from this new paradigm are Falcon, which is based on TPSF and lattices, and Wave, based on ATPSF and codes. And this concludes my example and my section.
Yeah, so the second half of our paper and our talk outlines the issues we've seen in the past with implementing these post-quantum schemes. And I think one thing we can say for sure is that the transition to post-quantum will be difficult. And we've seen that with some of the issues noted in the paper. And we know that post-quantum brings many new and unique challenges to implementing cryptography. We see new operations like Gaussian sampling, rejection sampling, and decryption failures, something we've not really seen in the past. One of the things we observed is that many initial post-quantum implementations failed in some key areas, which possibly wouldn't have happened if secure coding practices had been used. For example, ensuring that no leakage is present from data-dependent branching, which could have been bypassed by using things like CT grind. And we've also seen recent examples of implementation attacks on the Fujisaki-Okamoto transform, which is used in most, if not all, post-quantum schemes. One of the attacks exploits the use of a non-constant time comparison, and also another one looked at the errors of the in the domain separation of that operation. Yeah, we also in the paper looked at things on side channel analysis. So we consider things like power analysis on the core multiplication methods required for each family of within post-quantum. So, for example, matrix multiplication. And we also consider things like fault attacks, cold boot, key reuse attacks, and we also discussed things like how side channel hints can be incorporated in the security evaluation of the schemes. So there's papers that show this for lattice reduction and on codes using the ISD method. And as well as side channel analysis, we looked at the countermeasures. So we're looking at masking and hiding in post-quantum. And we obviously look at this so that we can put these post-quantum schemes in the wild. And it's another important area to consider. We've seen, we've only really seen the start of this though. So I think we'll see a lot more of this. So yeah, for post-quantum, we have 3 of the NIST candidates that have a masking scheme proposed. Kyber was really recent. And I think in general, post-quantum is also another challenge for masking is also another challenge for post-quantum. We see a lot of new operations like rounding and comparisons and things that make the masking awkward or difficult. And we've also seen recent results that show that these countermeasures are by no means a guarantee. Something we've seen a lot in the past for RSA and AES, and we'll likely see a lot more of these in the future as well. And one thing we also look at is this hedging technique for mitigating fault attacks in fiat-Shamir signatures, which is another interesting avenue of research. Finally, we look at benchmarking, like the projects that benchmark these schemes. So NIST in their call asked for performances in software and hardware and side channels in order to add some evaluation criteria to this competition. They decided on the ARM Cortex M4 and the Xilinx RTX 7 FPGA. There's plenty of repositories online for software benchmarking on the Cortex M4 and other CPUs. One thing to note on the M4 is that up to 50% of the time of not all, but a lot of these schemes are spent on seed expanding. And I think this actually goes up to 70% for some of the signatures. And we also collate a lot of the hardware designs that we've seen over the years on these candidates as well. So yeah, that's really the summary of the 2 chapters of the 4. So here's the ePrint link if you want to look at the others. And yeah, thank you for listening.
Hello and welcome to this talk about dual lattice attacks for closest vector problems with preprocessing. This is joint work with Michael Walter from IST Austria, and I'm Thijs Laarhoven from the Eindhoven University of Technology. So this talk will be about lattices. So just to start easy, so what is a lattice? So given basis vectors, in this case B1 and B2, we get a lattice from this by taking all integer linear combinations of these basis vectors, which in this case gives this infinite grid of points depicted in gray. You can use lattices to build cryptography, and this cryptography is only secure if certain lattice problems are actually hard, such as the closest vector problem, which asks to find the closest lattice point to a target point. In this case, this point T here, and the closest point would be this point V here. And in this talk, I will focus on the closest vector problem with preprocessing, which says that, okay, I first give you a description of a lattice, say, again, a basis, B1 and B2. Now you can do anything to it. So for instance, you can find a nicer basis for the same lattice, R1 and R2. Maybe you want to enumerate all short vectors. I mean, you can do whatever you want. Maybe store them in some data structure. But then when you say, okay, I'm done, then I will give you a target vector. So in this case, this point T here. And then again, you have to find the closest point to it, in this case, V. And hopefully you can do this faster than if you didn't do any preprocessing. Our paper is about dual attacks, but to put it into context, I will first consider primal attacks and to cover them briefly. So maybe the most natural approach that you can think of for solving this problem in high dimensions or any dimension is to use Voronoi cells, because Voronoi cells exactly tell you that if you are in one of these cells, then the point in the middle of the cell in the cell is actually the closest point. So in this case here, like if you are in one of these cells, then you know that the lattice point in this cell is actually the closest lattice point out of all lattice points. But okay, if you want to use these in high dimensions, like the first question is, how do you actually store these Voronoi cells? Where you can implicitly store them by storing the relevant vectors, which are in this case vectors R1 to R6, which define the boundaries of the Voronoi cell origin. And then you can also use these relevant vectors to build an algorithm for solving the closest vector column as follows. So if we have a target T here, this orange star on the right, then okay, in this case the closest point is this orange point on the right, and it's in the cell here. And what we're going to do is we're going to add relevant vectors to make it shorter and shorter until we end up in the Voronoi cell of the origin. So just to show what this means is that we add these vectors one by one, shifting it in the same coset of the lattice until we end up in the Voronoi cell of the origin. In this case, we cannot reduce it anymore. So we know that now the origin is actually the closest point to this shifted target, and that also tells us what is the closest lattice point to the original target vector. So this is actually the exact Voronoi cell approach, but this does not really work well in practice because the number of Voronoi cells or the number of relevant vectors is way too big to use this. So in this case, we have 6 relevant vectors, but in n dimensions, you have 2 to the n vectors to describe the boundaries of this Voronoi cell. And that is just way too much. What you actually do in practice, like what is currently the state of the art, is to use approximate Voronoi cells, where you say, okay, I'm not going to use the exact set of relevant vectors. I'm just going to use a short set of a small set of short vectors. So in this case, V1 up to V4, for instance, which again defines some kind of cell which looks like the Voronoi cell. And then using this approximate Voronoi cell, you can again use the same approach as before, where you reduce the targets all the way until you get into the cell of the origin. But now, because this approximate Voronoi cell is not an exact one, we may not actually find a solution, because in this case, the solution that we think we have is actually not the closest lattice point. But actually, if you randomize this procedure of reducing a number of times, then you may actually find the right representative in this approximate Voronoi cell for the origin, and then you do find a solution. So you have to run this a number of times, and then actually you do find a solution. So you use an approximate representation of an approximate Voronoi cell, and then you use that instead. But okay, so our paper is actually about the dual attacks and analyzing these and comparing it to the primal attack. So just to recall briefly, so what is the dual lattice? So the dual lattice is defined as all points in space for which the dot product with the primal vector is an integer. And that again forms a lattice. So in this example, this two-dimensional example, this grid of pink points is the dual lattice. And the dual of the dual is again the primal, which also means that the primal lattice can be defined as all points in space for which the dot product with the dual lattice vector is an integer. And this dot product has to be an integer for any dual vectors. Also, if you take, for instance, this dual vector D1 here, then we know that all primal lattice vectors must have a dot product which is an integer, which means that it must lie on one of these lines here. And because D1 is a short dual vector, these lines are pretty far apart. And that is the key property for the dual attack, which is the observation here that if we now have a target vector which does not lie on the lattice, on the primal lattice, but close to the primal lattice, then also it will lie close to one of these lines. So if we take the dot product with a short dual vector and we compute it modulo 1 to see if we are close to one of these lines, then we actually can distinguish between targets which lie far from the lattice and which lie close to the lattice. So okay, here so if you have a target vector, you can compute these dot products with dual vectors, compute them modulo 1, and then you combine them in a certain way for lots of dual vectors. And if you do that in this way here, for instance, with this cosine score, then you see that the output value tells you exactly how close you are to the lattice. Because like if you are very close to the lattice, if T is close to the lattice, then this infinite sum over all dual vectors is going to be very large, which is depicted by a darker shade of red here. Or if the sum is kind of small, like the target is kind of random in space, then you get like a white color. So you can tell from the value of this infinite sum whether you are close to lattice or not. But you have to take this infinite sum of all dual vectors, which is not really what you can do in practice. So what you can actually do in practice is you just take a number of short dual vectors and you again compute such a sum, and then you hope that this also helps you distinguish between targets which are close to lattice and which are not close to lattice. So in this case, if we take these 4 points here, then the shape is not exactly like this nice Gaussian shape around the lattice points, but you get like kind of a distorted Gaussian shape. And you can use this to distinguish. And you can also build a search algorithm on top of this by doing a gradient descent approach on this kind of hilly landscape with all these Gaussians around the lattice points. So you move in the direction of the gradient of this sum of cosines. So just to illustrate this, if we have this target T here, then we shift, like do a small step in the direction of the gradient, which means that we get this point T prime here. And then we do this a number of times until we get very close to lattice. And then we get our estimate for the closest lattice point to the original target vector T. In this case, we don't actually find a solution because we only have an approximate representation of the exact like Gaussian shape, because we only have some short dual vectors. So that is kind of the basic idea of the dual attack. And that is what we analyze, both the distinguishing and the search algorithm, this gradient descent approach. Okay, so just to illustrate the main results from our paper. So here we have on the horizontal axis, we have kind of different problem settings, where either we have a target which lies very close to lattice, which is the left part of this graph, the BDD setting, the bounded distance decoding setting. On the right part, we have the problem setting where we have a target which may be kind of random in space, but we are happy if we find any close-ish lattice point. Like we don't have to actually find the closest one, but something which is like at most effective 4 further than the actual closest vector is already a solution, which is on the right part of this plot. And then on the vertical axis, we have the query complexity. Like after the preprocessing, what is actually the cost of solving one CVP instance with this approach? So in the red, we have the primal attack, which we can see that it works pretty well for approximate CVP settings. Like if we want to solve approximate CVP problems, then actually a primal attack is what you want to use because the dual attack is not really going to help you so much. But if you want to solve a BDD instance, then actually the dual attack is much better, which is what we analyzed and what we showed. This is also kind of solving an open problem from the literature on the primal attack, where we saw that the primal attack works well for approximate CVP, but not for BDDP, which is kind of weird. And we were like, okay, maybe this is a problem with the primal attack. But now we showed actually the dual attack is much better here, and the dual attack does not work well for approximate CVP. So it's kind of these primal and dual attacks are kind of dual to one another, not just by using one the primal lattice and one the dual lattice, but also one works well for one problem and one works well for the other problem, which is kind of a nice result from our paper. So this is kind of the simplest result that I can present in this short time. So just to briefly conclude the main contributions of our paper and the end of this talk. So primal attacks, the approach here is that you use a list of short primal lattice vectors like this Voronoi cells, approximate Voronoi cells. And this works well for solving approximate CVP and CVP, but not for bounded distance decoding problems. While the dual attack uses a list of short dual lattice vectors, either to distinguish using the sum of cosine values, or to actually find a solution using this gradient descent approach. And this works well for bounded distance decoding with preprocessing, but not for approximate CVP, where the primal attack is better. And this work is actually, like our contribution is a complete heuristic average case analysis of the dual attack, which has not really been done before for CVP. Was mostly done for learning with errors, for instance. And we also did experiments with this approach, and these experiments closely match our heuristic predictions. Like it's not even just kind of close, it's really, we can almost exactly tell you what is the cost for like dimension 80. Like our theory is really very close to our heuristic predictions. So this is just kind of the high level results in our paper. So I will stop here. So yeah, thank you for watching.
Hello, and thank you for attending this presentation. I am Corentin Jeudy, and I'm a research intern at Université Rennes, CNRS, and IRISA. I will be presenting today a joint work with Katharina Boudgoost, Adeline Roulanglois, and Weichang Wen on the hardness of module learning with errors with binary secrets. Our work is focused on proving the hardness of the module learning with errors problem when using binary secrets. And we do so by providing a reduction from MLWE to its binary secret variant. The problem, as well as its binary variant, are fundamental in lattice-based cryptography because their structure allows for a nice balance between efficiency and security. The purpose of this work, more precisely, is to get a better understanding of the module learning with errors problem, and more specifically, of the differences between theoretical and practical hardness when using small secrets. The small secret case is particularly interesting for various constructions, especially for homomorphic encryption, as well as for efficiency reasons. And it is also valuable in the proof of some other theoretical results. Now, as far as the parameters go, I will just mention that the main restriction is about the module rank, which needs to be super logarithmic. We will see in a second what it refers to, but it is the most challenging part when trying to close the gap between theory and practice. But before, let me do a quick reminder on what this problem actually is. So you're given a uniformly random matrix A with M rows and K columns. M is called the number of samples, and K is the so-called module rank. You're also given a vector B of size M, and the MLWE problem asks you to decide whether B is uniformly random without any specific structure to it, or if it is of the form AS plus E, where S is a uniformly random secret vector and E is an error vector following a Gaussian distribution. As opposed to standard LWE, where we work over the integers, in MLWE we work over ring R. R here can be seen as the ring of integer polynomials with degree less than n, where our asymptotic parameter n is the degree of the defining polynomial phi. A popular choice of n for both theory and implementations is when it equals a power of 2, because it simplifies the form of phi, making it quite easy to work with, and it also has additional interesting properties to work with. The final parameter that I didn't mention is the modulus Q. All the matrices and vectors are composed of elements of RQ, which can be seen as integer polynomials of degree less than n still, with each coefficient is reduced modulo the integer Q. But what interests us today, more specifically, is the binary version of this problem. The only difference is that instead of choosing the secret vector S from RQ, we choose it from R2, which essentially is the set of vectors for which each coefficient is a binary polynomial of degree less than n. Now, the reason why MLWE is so interesting from a theoretical standpoint is because it subsums two of its popular variants. First, the original LWE problem can be seen as a special case of MLWE when setting n equals to 1, because then we fall back on the integers. The second is the ring LWE problem, which was the first structured variant of LWE, and which is quite popular for its efficiency. And here, ring LWE corresponds to the case when the module rank K is equal to 1. But why else do we care so much about this problem? Well, from standard LWE, we were able to construct several cryptographic primitives ranging from public key encryption to signatures up to the more advanced ones like fully homomorphic encryption. And although these schemes are secure, they lack of efficiency. Now, on the contrary, the schemes based on ring LWE are more efficient, but we still have some doubts about their security. And this is where MLWE becomes interesting because it allows us to tune the parameters to trade concrete security for efficiency and vice versa. So much so that 3 of the third round finalists in the NIST competition use it as their hardness assumption. The Crystal Suites, for example, bases its security directly on the hardness of Module-LWE, while the key encapsulation mechanism Saber is based on module learning with rounding, which is a deterministic variant of MLWE. And according to the NIST, these structured lattice schemes seem the most promising candidates for the post-quantum cryptography standard as far as KEM and digital signatures go. And in all of that, the binary version is mostly helpful because these candidates prefer to use small parameters to make the schemes more efficient. And this is why we need to investigate the theoretical framework behind it to back that up. So we can now dive into the core of our work, and here's an overview of the different steps of our reduction. We first reduce MLWE to a variant called first is errorless MLWE. It is exactly the same problem except for an extra hint on the error vector E, which is simply the first coefficient of the vector E. Then we reduce to another variant called extended MLWE, where we generalize the possible hints on E by allowing any binary vector Z. We then go to a matrix version of the same problem. So we have a secret matrix and an error matrix, N, but the rest is exactly the same. And finally, we reduce to MLWE with binary secrets. So in the remaining time of the presentation, I want to focus on two steps here. The first one being the reduction from first is errorless to extended MLWE. In this step, we need to explicitly construct a matrix over the ring. For each binary vector Z, we must construct a matrix U that is invertible mod Q, and such that all of its columns, except for the first one, are orthogonal to the vector Z. We also need to minimize its spectral norm because it is what influences the noise growth of the reduction, so we want to keep it as small as possible. So we provided this construction here, which looks rather simple. The orthogonality is quite trivial due to this plus negative pattern of the columns. And the spectral norm can be bounded quite easily as well because of the diagonal structure of the matrix. The tricky one, though, was the invertibility condition because it requires every diagonal element to be invertible in the quotient ring. Fortunately for us, we were able to use a recent result by Lubashevsky and Saylor from 2018 that gives explicit conditions on Q to provide us with the invertibility of small norm elements, which we can use for binary elements as well. And this is what completed our construction. The second step that I want to focus on today is the final reduction to binary MLWE. In this step, we use a lossy argument, which consists in replacing the matrix A by an MLWE instance, BC plus N, where C acts as a secret matrix and N as a Gaussian error matrix. And the goal here is to prove that the top two pairs are indistinguishable to prove that the problem is hard. So we start by decomposing the error E into negative N times Z plus E hat, where both N and E hat are Gaussians. And then we replace A by BC plus N. Now, the reason why we need the extended MLWE hardness assumption is because we have some information about N times Z in the previous pair. So we need to include this hint within our hardness assumption. After that, we use the ring version of the leftover hash lemma to argue that C times Z is indistinguishable from a smaller vector S, which is uniform mod Q. And this is where our superlogarithmic rank condition is needed. Then BS plus E hat is an MLWE instance. So assuming that MLWE is hard, we can say that it is indistinguishable from a uniform vector B. And finally, we map A hat back to A using a similar assumption, which concludes this whole chain of indistinguishability, proving the result. So to briefly conclude, I first want to mention that our work extends the result from the original paper by Brakerski, Langlois, Bijker, Grigev, and Stille from 2013, which deals with standard LWE. So if we set n equals to 1 in our setting, we end up with the same result as theirs. We also provided another reduction at Asia Crypt last year, which achieved a similar rank in modulus conditions, but the noise growth was a little bit larger. So here we managed to improve that by a factor of square root m times d, also making it independent of the number of samples m, which is quite satisfactory as well. There are still some open questions, the main one being about the existence of such a reduction for smaller ranks. We required the module rank to be super logarithmic because of our leftover hash lemma, but it would be interesting to have a similar result for constant ranks because it would encompass most practical constructions, including the NIST candidates that I mentioned earlier. The case d equals 1 would also be particularly interesting, as it would provide the first result the first hardness result for ring LWE with binary secrets. Finally, even though other number fields are not common in cryptographic constructions, it could be interesting to extend our result to other number fields than cyclotomics, but just out of pure curiosity. Thank you for your attention, and I'll be there in the interactive session if you have any questions. Thank you.